All right, so what I'm going to do is we're going to talk about how nuclear reactors work today. Okay. And I might go all over the place first. I want to make sure that you understand the basics of it or the fundamental principles of a nuclear reactor. And then we'll go over the slides. Okay. And I've changed the slides a bit, so I'm going to upload the latest slides after class. Okay. All right, so here is the nuclear reactor. You take a heavy nucleus, in this case it's uranium-235 that we use in reactors. Here's a neutron. You shoot this neutron at the uranium-235 nucleus. It breaks up into two large chunks. So this is roughly 240 units. So these guys are about 120 units each. Okay? They're made of protons and neutrons. And in addition, 3 neutrons come out. Plus energy. Energy is mc squared. And this is about 200 MeV. And we'll come to those numbers in a second. Okay. First, let's answer, why is energy released? When this nucleus split, why is energy released? You guys understand the question? Okay. So that's at the heart of nuclear energy. So we want to understand that. So anytime energy is released, the products, these guys, weigh less than the ingredients. Okay, that's the first basic principle. Anytime energy is released. Okay, so for instance, you can burn coal. Coal is carbon, okay, O2, you get CO2, okay? And plus energy. So the same principle applies. When you burn coal, these are the ingredients, this is the mass of the ingredients, there's the mass of the product. If energy is released, the product weighs less than the ingredients. Okay? Except that when you burn 1 atom of carbon, you release about 4 eV of energy. What does MeV mean? Million electron volts. So you split 1 uranium nucleus, you get 50 million times more energy than when you burn coal. Okay? Did you guys understand that? I mean, that's a lot more. What is the other benefit that you see? No carbon dioxide. Remember, this guy is your enemy. So no carbon dioxide. So nuclear energy is pretty good. All right. Come on. All right. So we learned that why is energy released? Because these guys weigh less. Okay. So the products weigh less. Why do these guys weigh less? Very good. So all the nucleons are more tightly bound. Okay. And you saw that in this graph from last chapter. You saw that this is the mass of a free proton and a neutron. In a uranium nucleus, each proton and a neutron weigh that much. Okay, so if this was 100 units, that's about 95 units. But in the smaller pieces, they weigh even less. So that missing mass is what gets converted to energy. Okay. You saw that in a nuclear reaction, a lot of energy is released, and that's why we like it. All right. So you guys understand basically where the energy comes from. Okay. Now, okay, so this energy is released. How is it released? It's released as heat. Okay, what do you do with the heat? Let's see what we can do with the heat. So I'll show you what we do with the heat. So again, so here's what we do with the heat.
Outer ends are internally attached. The two rings R1 and R2 are internally attached. The two rings R1 and R2 are internally attached.
Okay, so what we want to do is, so you saw, you guys can go ahead and see this simulation, but if you turn that piece of wire that's sitting between magnets, the energy you spent in turning the wire gets converted to electricity. This device, the generator, is converting mechanical energy into electrical energy. You guys understand that? So how do you turn that wire? You use the heat generated in the nuclear reactor to produce steam. That steam is what's turning this wire. Okay, so that's the goal. Did you guys understand that? Look at the pieces of a nuclear reactor. All right, so now let's okay, so now, so here is the nuclear reactor. So here is the fuel core. The fuel has the uranium-235. You know how to split it. Every time you split a uranium-235, heat is generated. What you do is you pass water through the core. Okay, that gets converted to steam. The steam is turning a turbine. It's turning blades in a turbine. And what is that turbine doing? It's turning that piece of wire in the electrical generator. Did you guys understand that? All right. Any questions?
I have a question.
Okay, go
This
ahead.
might sound really stupid.
No.
But
Mhm.
you've like talked before about like nuclear energy and like taking a car and like turning it into energy, right?
Mhm.
That's not exactly what nuclear energy is. We're taking chemicals and changing them. Like I'm confused on that.
No. So in nuclear energy, okay. So
So you're
you're
not actually taking objects and like turning them into energy, right?
all right. So hold that thought.
Okay.
This is Einstein's equation. Okay, what Einstein's equation tells you is c is the speed of light, m is the mass, E is the energy. Okay. In everything, any energy conversion, well, you're converting mass into energy. Okay. So how are you converting mass into energy? Okay, so you take ingredients and you form a bound state, and the tighter this is bound, the less it weighs. Okay. So everything you do, you're trying to make it more tightly bound. In a chemical reaction, well, it is more tightly bound, except that it is not as tightly bound. Okay, so the mass decreases a lot less. Okay, then if you take a nucleus and break it into pieces, these guys are much more tightly bound, millions times more tightly bound, and that's why you get a million times more energy released. Okay, so in a nuclear energy, you're converting a lot more mass into energy than in a chemical reaction.
Okay.
You're not convinced, but
I just maybe it's because of your analogies that have kind of like confused me.
okay. All right.
To make that analogy more clear with the
Mhm.
car thing,
Mm-hmm.
are we assuming the car is made of uranium, or are we condensing the atoms down to uranium?
Okay, so let me. Okay. To convert mass to energy, you have to have some process. If you burn something, this is a very simple analogy. I mean, very simplistic analogy, and it's made up. So when you burn something, all you're doing is maybe rearranging the electrons from a higher level to a lower level. And then very little mass is converted to energy. Okay? So we don't want to do this. This is chemistry. Okay? We want to aim for bigger things. So what we want to do is mess with the nucleus. Now, if you take a large nucleus and split it into two nuclei, see, the number of protons and neutrons are the same. It's just that when you break this up into smaller pieces, there the neutrons and protons are more tightly bound. And so the amount of mass converted to energy is a lot more, millions of times more. And that's the point of nuclear energy. Okay.
Still don't understand what tightly bound means.
Tight.
I know what that means, but I don't know what it means here.
Okay, so let's use a big example. So here's the sun, here's the earth, there's the earth's orbit. Now if you take the earth and put it in Mercury's orbit, it's more tightly bound.
What's more tightly bound?
The earth and the sun system.
Force is stronger, right?
The force is stronger, okay? They're closer, and so on. Okay, so what that means is the following. So here's the sun and the earth. We'll make some numbers up. Let's say the sun, you went to the store and bought the sun, it's 1,000 units, and the earth is 100 units. What is this solar system? What's the weight of this solar system? 1,100, less than that, okay, less than 1,100. Okay, and that's why, so let's say it's, I'll make up a number, 99, okay. Okay. So if you want to break this up, you have to put in 1 unit of energy. Okay. Did you guys understand that? And it weighed less because it was more tightly bound. It was tightly bound. Okay, now we take the same sun and the earth, except that we're putting it in the Mercury's orbit, Earth. And now this guy weighs 95. It's more tightly bound. So to break this up, you have to put in 5 units of energy. And that's what tightly bound means. Okay? Did you guys understand that?
Sure.
No, not quite. You see, the thing is, in everything we do in a nuclear reactor and stuff like that, you can take a proton and a neutron. You can't make this proton completely into energy. You can't convert it completely into energy. Okay, so let's say this proton weighs 100 units. You can't completely, if you wanted to do that, you would take a proton and an antiproton and then completely convert it into energy. But that's not practically possible. Okay. So the best we can do is, here's a proton. Okay, so here's a proton. Okay, a free proton is 100 units. Okay, in uranium, the proton weighs 95 units. Okay, so again, I'm making this number up. But in this smaller nucleus, the proton weighs 92 units. Why does it weigh less in this piece, in this nucleus? Because it's more tightly bound. what happened to this difference in energy, in this difference in mass? That got converted to energy. And that's the best we can do. And that's at the heart of the nuclear reactor, how to split this guy into these two pieces. Okay? And to sustain that reaction. Yeah. So even at the end of the day, you converted 2% of the mass into energy. You didn't convert 100% of that mass into energy. Okay? So all we can do is about convert 2% of that mass into energy. And we can't do that for the car. It has to be uranium. But what I'm saying is the equivalent of if you can convert 4,000 kgs into energy, you can run the world for a year. That's what I'm saying.
Okay, so the nucleus that's being broken up is in one of, like, something from the periodic table?
Yeah, it's
I
the
think
uranium.
that's what the question was. Like,
Okay.
we're not taking real objects and turning them into energy. We're taking that stuff.
Right.
Okay.
And not just any nucleus. It's uranium and not this particular isotope of uranium.
So it can only be uranium?
Right now, most of the reactors are set up. There are other elements that you can use, but I mean, other, again, plutonium and we'll see thorium and all that. Okay, so right now we're just taking uranium-235. And you know, uranium-238 is the 99.2% is uranium-238, and uranium-235 is only 9.8%, roughly, something like that. Okay, so this isotope is what we need.
Would you be able to make that isotope that's right here?
I'm sorry?
Would you be able to make
No. All right.
Where do you find uranium?
Well, the uranium is available all over the world. It's so Australia has 28% of the uranium. Canada 9%, Kazakhstan 15%, and so on. Yep. But then we can use other fuels. Okay, so let's. Okay, maybe you want to ask questions because this is a fairly cool technology, and get it all out. Yep.
But they have the rods there, how do they control how many reactions are happening at a time?
Okay, so we'll come to that. Okay. All right, so now let's build up. Okay, so again, you take a uranium-238 nucleus, shoot a neutron, the neutron gets absorbed, it becomes unstable, it breaks up into two pieces, and then splits out 3 neutrons. All these things weigh less than these two guys, and that missing mass is converted to energy. Yep. And again, the great thing about this is when you split one uranium nucleus, you're getting 200 million electron volts of energy. When you burn one carbon atom, you're getting 4 electron volts of energy. This is 50 million times more. And why is that? Because these guys weigh that much less. Because they're that tightly bound, because it's a nuclear force that's involved, a strong force. Yep.
Where are they pulling that original neutron from?
They're floating around. You can go buy a neutron gun. We'll show you. Okay. You can have neutron sources, stuff that's spitting out radioactive material that are spitting out neutrons, but that's not an issue. All right, can you run the world on this? No, you need to keep producing energy. So here's the neat thing. So now we can use one of these neutrons to split the next nucleus. Okay? And you can keep a chain reaction going and split more and more nuclei and keep producing energy. Now here's the deal. If on the average, one neutron produces a further reaction, you can maintain that reaction. If less than one neutron produces a reaction, that reaction will eventually die up. Right? That makes sense. You split you use one neutron to split a nucleus, and then if this guy splits another nucleus, and that guy splits another nucleus, you can maintain that chain reaction. So if less than one neutron produces a further reaction, that reaction will die up. If more than one reaction produces, that's an atom bomb.
Is that like one of what the dangers are when it comes to?
No, that's not the danger. No, that's not the
There's no
danger.
dangers when it comes to this type of energy?
I'm sorry?
Are there no dangers when it comes to this type of energy?
There are dangers, but I'll come to the dangers in a second. But let's address your concern. According to some opinions, okay, so this is the relative risk of energy production, overall death and stuff like that. If producing electricity by coal has a relative risk of 100, by nuclear reactors it's 0.3. Yeah. So it's essentially riskless. Okay. All right. So all accidents essentially happen like this. So here are three accidents that have happened: the 3 Mile, Chernobyl, and Fukushima. Okay. So essentially, here's how all the accidents happen. Okay. So you have a nuclear reactor. So in this fuel, these are the fragments that were created. These are radioactive. So these guys will produce heat. They're radioactive and they'll produce heat. So even if you shut down the nuclear reactor, the used fuel is producing maybe about 5% of the heat that a operating reactor is producing. Okay. So this is still hot for a long time, and you got to remove that heat. What happens if you do not remove the heat? Okay. So we'll talk about how to shut down a nuclear reactor. So here's water. Here's water that is cooling this, removing the heat from here, and steam is coming. Okay, these control rods, if you put the control rods in, you can shut down the reactor. Now, if you shut down the reactor, those fragments are still producing heat. So you still have to constantly remove the heat. So you can't shut down these pumps. And all accidents happen so these pumps have to work 24/7, 365. In Fukushima, these pumps, okay, now we have designs where you don't need that. But if you're not removing that heat, the water eventually splits into hydrogen and oxygen. And hydrogen is explosive. And that's where all the accidents happen. Okay. Did you understand that? Okay. So we have designs where we can fix that. All right. So here are the issues of a nuclear reactor again. I'm going to keep repeating this 100 million times, so you'll at least remember it, whether you understand it or not. Right. So we're going to take a heavy nucleus, split it with a neutron in these two pieces, which are half. The neutrons and protons are more tightly bound, and that's converted to energy. What you want in a nuclear reactor is one of these guys to cause a further reaction, to maintain that chain reaction. Less than one neutron causes a reaction, then the chain reaction will die. If more than one neutron causes a reaction, it's an explosion. That's an atom bomb. Okay? So you have to absorb these other two neutrons. You don't want either, you have to absorb them or they have to escape. Okay? And the control rods do that. Okay? So again, in a nuclear reactor, you only have to make one neutron to cause a further reaction. Okay? All right, yep.
So does that mean that they only shoot neutrons from one rod to the other rod? They don't shoot them down the rod?
No, okay, so yeah, we'll come to that. Yeah, yep.
So I'm understanding this right. You said you have to get rid of 2 out of the 3.
Either, let them escape or absorb them.
But you have 2 split. Does each split need an extra neutron, or is one good enough for both?
Oh, so this guy, okay.
In order to split those 2 again.
No, those, you're just splitting a nucleus one time. Okay, let's,
Gotcha.
okay. So here's the uranium-235. You used a neutron to split them into, this is barium-141 and krypton-92. And one of these neutrons is splitting another uranium-235 nucleus. This is, the protons and neutrons are more tightly bound here. You can't do anything out of this. You're not getting any more energy. Yeah, okay? Now here's the deal. So you guys understand this so far? I'm just telling you pieces of the story. I don't think I'm going to get through the slides. You're going to read the slides on your own. Okay. Yeah. All right. Here's the deal. When you split this nucleus, these neutrons, all this, the energy released is in the heat in this, in these guys are hot. Okay, they're moving about fast. These guys are moving at about 20,000 kilometers a second. That is, they're going around the Earth once in 1 second. That's how fast they're moving. Yeah. Now you want this guy to cause another reaction there, right? You guys want this to split this nucleus. All right, let's look at this guy. He's moving at 20,000 kilometers a second. So when he comes out of the reactor, see neutron energy from fission, that's how fast it's moving. So this is neutron energy, and this is fission cross-section. What is the probability of him causing fission, further fission? Okay. So when he's moving extremely fast, if the cross-section of him causing fission is that much, but now if you get that neutron to slow down, the probability of causing fission can be increased 100-fold. Did you guys understand that? That's what this graph is telling you. Okay. You got to understand the pieces. All right. So these neutrons that come out, they're fast. Okay. Let me give you the speeds. Okay, well, anyway, they're coming out at 20,000 kilometers, and what you want to slow them down to is about 2 kilometers a second. So the probability of them causing fission here is much higher. Okay? And that's the job of a moderator in the nuclear reactor. Okay? So what do the moderator do? Moderators slow down neutrons so that these neutrons, when they're slow, the probability of them causing a further fission increases. Okay. All right, so let me show you the so here are the components of a reactor. Okay. Fuel assembly. Fuel, what is the fuel in your nuclear reactor? Uranium. Very good. Thank you, my friend. Okay. So you have uranium-235 as the fuel. Moderator, what does the moderator do? That's right. So when you split a uranium-235 nucleus, you get 3 neutrons. They're coming out very fast. For one of the neutrons to cause a further reaction, you want to slow them down. Okay, so that's what the moderator does. Okay. Water is a moderator. Okay. Control rods, what do control rods do? Okay. These are control rods. So and here's a control rod. There's the fuel assembly. If you drop all the control rods, they'll absorb all the neutrons, and the reaction will stop. Okay? So you won't have enough neutrons causing further reactions. Okay? So let's say you shut down the nuclear reactor, just drop the control rods. Is any more heat being generated? Where's the heat being generated?
From the already.
From the spent fuel, from the already existing pieces. How much heat is being generated? About 2 to 5%. So heat is still being generated. That thing is still hot. So you got to keep cooling it. If you don't cool it, if you use water as a moderator, that heat will split the water into hydrogen and oxygen. Hydrogen is explosive, and that's where you cause accident. Okay? So the three components are fuel, moderator, and control rods. Okay?
Is uranium a gas?
It's a solid.
What does it look like?
Uranium ore for sale. Yeah. All right, so we understand sort of, I mean, it's very cool technology. And so now we can design stuff. Again, so just so we do not forget, splitting one nucleus gives you 50 million times more energy than burning one atom of carbon. And in addition, the biggest benefit is no CO2, no greenhouse gases emitted into the atmosphere. Yep. Yep.
To be clear, without a moderator,
Mm.
it will not create more reactions, or it will create more reactions?
Without a moderator, it creates more reactions. It's just that with a moderator, the probability of the neutron creating a further reaction is higher. In fact, 99% of the reactions are created by the fast neutrons. Okay, that's the design, but we'll come to that point. Okay. Again, it's not an easy thing, but you can understand it if you pay attention for 50 minutes. Okay. And if you keep asking questions. All right? Are we good? All right. So I'm just going to go over the slides, but again, like I said, you guys will be mostly reading. Our ultimate goal is, here is an electric generator. What is its generator is a wrong word. It's not generating electricity. What it's doing is, so again, here are the magnets. Here's the wire. If you turn the wire between the magnets, what is happening is the energy you're putting in turning the coil is getting converted to electrical energy. So with this setup, you get an AC current. Okay. How are you turning this wire? A windmill, the wind is turning the blades, which is turning this wire. In a dam, the flowing water is turning this wire. In a coal power plant, you're burning coal, the heat released is used to boil water, and the steam is turning this coil. In a nuclear power plant, you're splitting nuclei. The heat is used to produce steam, which is turning this coil. So ultimately, your goal in life is to turn this coil, which is placed between magnets. And whatever energy you put in turning is getting turned into electrical energy. You're not creating energy, you're just converting one form of energy to another form of energy. In a windmill, the energy of the wind is converted to electrical energy. In a dam, the energy of the water stored at a height is converted to electrical energy. In a coal power plant, the chemical energy of the coal is converted to electrical energy. Why are you doing that? You're converting everything into electricity because it's easily transported. You can produce electricity in California and use it here and stuff like that. Okay? And stuff operates more efficiently with electrical energy. Okay? All right, so you guys understand that? So ultimately your goal is to turn that piece of wire which is sitting between magnets. Okay? Solar cells operate differently, and we'll learn about that in a couple of chapters. Okay? Okay. So fission energy, you're taking a heavy nucleus and fissioning it into two fragments. And the reason you did that was when you break it up into two pieces, in this smaller nucleus, the protons and neutrons are more tightly bound, they weigh less, and that missing mass got converted to energy. Okay? Maybe about 1% of the mass got converted to energy. So what we are saying is if this weighs 100 pounds, these two pieces together weigh 99 pounds, and that missing mass got converted to energy. Okay. Everybody understand that? And again, can somebody tell me why do these guys weigh less? Because they're more tightly bound. All right. All right. So these are just terms. Again, endothermic reactions they need energy to proceed, and exothermic reactions release energy. So what kind of a reaction is this? This is an exothermic reaction. This releases energy. This is also an exothermic reaction. It releases energy. Anytime anything burns, it's an exothermic reaction. Okay. Okay. So uranium-235. Okay. So here's a uranium rock, okay, or uranium ore or whatever. Yeah. And this guy contains 99.3% uranium-238 and 0.7% uranium-235. Okay, so you can't just take that and throw it in a nuclear reactor. You have to enrich this, depending on the design of your nuclear reactor. You enrich it to, let's say, and for example, the nuclear reactors in subs and all used in submarines, they have much higher enriched uranium, okay, because they're got to be smaller and all that. The ones we use are about 3 to 5% enriched. Okay, that means so the uranium is enriched such that about 5%, let's say, is uranium-235. Okay, again, you're going to split this into these pieces. These guys weigh less, and the missing mass is converted to energy. How much energy is released? About 200 MeV. Okay. So this graph is sort of the inversion of this graph. This graph upside down. Okay. So you took a heavy nucleus, split it into nuclei, and the binding energy per nucleon is greater, meaning they're weighing less. So again, okay. All right, when a neutron passes near a heavy nucleus, for example, uranium-235, the neutron may be captured by the nucleus. It doesn't have to be captured every time. Okay. In certain cases, the initial capture is rapidly followed by fission. Okay. So it might capture it, it might spit it out. But it might capture it and then it might split up. Okay. So all those processes are random. Yeah. And what you're in a nuclear reactor and everything you do, you're trying to make sure that the chain reaction is maintained. Okay. Fission may take place in any heavy nuclei after neutron capture. Okay. Low energy neutrons cause fission in an isotope of uranium and plutonium whose nuclei contain odd number of neutrons. Okay. So U-235, so low energy neutrons can cause fission in these guys. Okay, so even though uranium-238 is not fissionable by thermal neutrons, what you can do is you can use uranium-238 to produce plutonium, and that you can use in nuclear reactors as a fuel. Okay, so we'll come to that. All right, neutrons released in fission are initially fast. They move about 20,000 kilometers per second. Okay, but fission in U-235 is most readily caused by slow neutrons that are moving at about 2 kilometers a second. Okay, so what is this saying? What is that point saying? It's saying that when you split a uranium-235 nucleus, these guys are moving at 20,000 kilometers a second. But for this guy to cause a further reaction, a chain reaction, you need to slow this down from 20,000 kilometers a second to 2 kilometers a second. And who's going to do that? The moderator does that. Okay? All right. A moderator material comprising of light atoms surround the fuel rod in a reactor. It must slow down the neutrons. Okay, so so here's a reactor vessel. This is the moderator. This is just bathed in water, and water acts as a moderator. Okay, yeah. So water is one of the moderators, and so the neutrons are coming out and going about randomly fast, and the moderator slows down, and one of those slow neutrons can cause further reaction.
You would think water would speed things up though, right?
All right, so here's the idea. I have a whole bunch of ping pong balls that are moving about fast. If the ping pong ball hits a bowling ball, will it slow down? Will it transfer any energy to the bowling ball? No, it won't. Now, you have a whole bunch of ping pong balls, and then you have a bunch of other ping pong balls, blue ping pong balls and red ping pong balls. When blue ping pong balls are moving fast and these red ones are stationary, when a blue one bounces off a red one, it will transfer energy to it, and that will slow it down. Okay? So if you have a bunch of particles moving fast, if you want to transfer energy to lose energy, you have to collide with somebody of equal mass or less. Okay, that's the idea. So that's where we said the moderators have to be light atoms. Okay? See, you guys are understanding. Okay? And you know what's your homework going to be? Go build a nuclear reactor today. Okay? Okay, so a moderator material comprising light atoms surrounds the fuel rod in a nuclear reactor. Okay? And what is its job? To slow down neutrons. Okay? Okay, so in a nuclear reactor, when a neutron is captured, the energy of the nucleus is unstable and breaks up into two fragments of roughly equal masses. The fission process is followed by an emission of 2 to 3 neutrons. The fission process is followed by an emission of 2 to 3 neutrons. These neutrons cause further reaction, making a chain reaction possible. So this will cause another reaction, which will cause another reaction, and so on. Okay? And a chain reaction is maintained. Okay? Now, this is a minor point. No, well, not minor point. I mean, it's in a sense important. Why are 2 or 3 neutrons being emitted? These were crucial to maintain a chain reaction. Why did these guys spit out 2 or 3 neutrons? So let's understand that. Okay? You guys understand what I'm trying to say? Okay, let's figure out why these guys are spit. Okay, and so what does this graph tell you? See, these are the stable nuclei. Okay? So what is this? This is the number of neutrons in the nucleus. This is the number of protons. Z is the number of protons. Okay? So you see, what this graph is telling you is if you have a smaller nucleus, okay, the number of neutrons is equal to the number of protons. But if you make a heavy nucleus, the number of neutrons has to be much higher. So when you split a heavy nucleus into smaller pieces, okay, you don't need as many neutrons. Okay, in a heavy, big nucleus, so protons are red, neutrons are blue. In a heavy nucleus, you need a lot of neutrons to keep the protons apart. But when you break it up into 2 pieces, you don't need as many bouncers. You guys understand? Does that make sense? And so there are always extra neutrons and you split them up. Yep. Yep.
So the amount of neutrons that are spit out isn't always 3?
Yeah, it's whenever you go to the atomic level, everything is random. It's a probability thing. So on the average, 2.45 neutrons are split up. Yeah. So between 2 and 3. And we'll come to this. Here's a very crucial feature. Okay. Oops, the wrong slide. Okay. So most of these, 99% of these neutrons are spit out within a billionth of a second. If every one of them was spit out immediately, so those are called prompt neutrons, if all of them were spit out within a billionth of a second, you couldn't build nuclear reactors. All you could do is build bombs. Less than 1% are spit out, so they're unstable and they'll spit out the neutrons. They're spit out with a half-life of 10 seconds. And that's what allows you to put in and down, so lower the control rods. Okay, so again, if all of these guys were prompt neutrons, if they're spit out within a billionth of a second, you could not build nuclear reactors. All you could build was atom bombs. Okay, because about 1% are delayed neutrons, you can build nuclear reactors. Okay.
Are delayed neutrons caused by the products of the uranium, or are they?
Yeah, no. All those neutrons are split by the product of the uranium.
How come every time we split the nucleus, it was always like, if it was 100, then it would be like 99 on each, but then in the pictures, it's always showing different amounts after it's.
Well, when this splits, it never. Okay, so here, so when it splits, it never. I mean, the 2 pieces are different. So this is the probability curve of what the pieces are. The highest probability is for these 2 pieces, but when this, you can have this piece and this piece and this piece and that piece and so on.
So they're not always gonna weigh the same, in what,
Well, the total number of protons and neutrons are going to be the same.
those are the same,
Yeah,
but the chemicals are different.
right. And these pieces are radioactive for about 10,000 years. That's the only problem yet. And to give you an indication, that's not much of a problem. All the commercial reactors, so we have had nuclear energy for about 60 years, 70 years, 60 years. I'm not talking military applications. I'm talking just commercial electricity production. There's about 450 nuclear reactors in the world, all the commercial reactors. The nuclear waste produced can be contained in this building. Not a problem at all. You just go bury it in your neighbor's yard. All right. All right. So again, what is so? Okay, so moderator comprising of light atoms surrounds the fuel rods in a reactor. Okay. In a reactor using natural unenriched uranium, the only suitable moderators are graphite and heavy water. Heavy water is, here's ordinary water, so you'll hear heavy water, D2O, okay? So D is a, okay, this is hydrogen, and this is an isotope of hydrogen. And this is called deuterium. Okay, so this is a proton and a neutron, and there's the electron. Okay, so this guy is twice as heavy as hydrogen. So this isotope, and if you use that to produce water, that's heavy water. Okay. So again, moderators are important to slow down neutrons, right? Okay, so depending on what your fuel is, you use the moderator. Moderators are graphite and heavy water in unenriched uranium. With enriched uranium, ordinary water may be used as moderator. Okay. Water is also commonly used as a coolant to remove heat and generate steam. Okay. The fission process is followed by an emission of neutrons. On an average, 2.45 neutrons are emitted. Okay? Of course, you're not emitting a fraction of a neutron. Some reactions emit 2 neutrons and others emit 3 neutrons. Okay, so here's where all the accidents are. About 6% of the heat generated in the reactor core originates from radioactive decay of fission products and transuranic uranic elements formed by neutron capture. We'll come to that in a second. And these guys, the heavier, these are called actinides. These guys are radioactive for maybe 100,000 years. Okay. So even if you shut down the nuclear reactor that has been operating, you're still generating heat. Okay. This must be allowed for when reactor is shut down, since heat generation continues after fission stops. And if you don't cool it down, what happens? If you're using water as a coolant, that heat will eventually split water. Hydrogen is explosive, and that's bad news. Okay? Bad news in the sense that it'll explode parts that you don't want to explode. Yeah.
What happens if you take out all the coolant?
I'm sorry?
What happens if you take out all the coolant? The moderator.
The what?
What happens if you take out the moderator?
Oh, well, no, the moderator, then the chain reaction won't be sustained, because if you take out the moderator, well, hopefully the moderator and the coolant are not the same. If the moderator is taken out, it's not slowing down neutrons, and they're not causing further reaction. They're causing reaction with a lower probability, so the chain reaction would die down. But you never want to remove the coolant. I mean, the coolant needs to keep going. But now we have designs where that's not an issue. Even with coolant turned off, we'll shut down the reaction. Okay. It is, this must be, so So about 6%. This must be allowed for when the reactor is shut down since heat generation continues after fission stops. The radioactive decay of used fuel generates heat and hence needs cooling. In the Fukushima accident, when cooling was lost an hour after shutdown, the used fuel was still producing about 1.5% of the full power heat, leading to an explosion. Okay. So that's the problem. Even after 1 year, a typical used fuel generates about 10 kilowatts of decay heat per ton, decreasing to about 1 kilowatt ton after 10 years. Yep.
So after shutting it down, would you have to continue to cool it for 10
Yep.
years?
Yep. Mhm. So, again, they put it under pools of water and stuff like that. Anyway, but all this technology is simple. And why do we strive for this? What's the best thing about this?
There's
No CO2. Very good. Okay.
So are the control rods that we were talking about earlier,
What do the control rods do?
are they like ice cubes? Like,
No. They're materials. They're materials. What do control rods do? I don't know. Tell me, what do control rods do?
control the
Hmm?
mechanism.
Stop the neutrons from.
They absorb neutrons. Okay, so control rods are made of materials that absorb neutrons. Okay. Why do you want to absorb neutrons? You just want to make sure one neutron causes a further reaction. Okay. So we'll come to materials that are control rods. Okay. Okay, so delayed neutrons, you want to understand this. Okay. Following fission, over 99% of the neutrons are emitted immediately, immediately meaning within a billionth of a second, called prompt neutrons. The delayed neutrons come from the radioactive decay of certain fission products. Okay. So, these are fission products, and the delayed neutrons come from them. Okay. Come from radioactive decay of certain fission product. The longest delayed neutrons group has a half-life of 56 seconds. Delayed neutrons are crucial factors enabling a chain reaction system or a reactor to be controllable and to be held precisely critical. What does that mean? Precisely critical? A donut to whoever answers it correctly. I'll have to buy it because I ate the donut you brought.
I already had 4.
Oh, you already. Well, next week you would have. What does precisely critical mean? One further neutron is causing a reaction. If 0.99 neutrons are causing, that's less than critical. Okay, you're not maintaining the reaction. Okay. Fission of U-235. One of these neutrons is needed to sustain a chain reaction. The other leaks from the core region are absorbed in non-fission reactions. They're absorbed by control rods. Okay. Neutron absorbing control rods are used to adjust the power output of the reactor. So these typically use boron or cadmium. Okay. Both are strong neutron absorbers and are inserted among the fuel assemblies. Okay, again, energy released in the fission of a nucleus is about 200 MeV. Contrast this with 4 eV per atom of carbon burned in fossil fuels. Okay. So you're getting 50 million times the energy per atom. 50 million times. Okay. So this shows you the pieces it breaks up into. Okay, so these two pieces are the most likely, but again, the total number of protons and neutrons are the same after the breakup. Okay. So typically one fragment is about 90 nucleons and the other fragment is about 140 nucleons. So these fragments almost always have more neutrons than required for a stable nucleus, and they either emit neutrons or beta decay. So they emit neutrons, Okay, that's how come we have those 3 neutrons. Yeah. Stable chain reaction. So what does that mean? So you split this uranium-235 nucleus, and you have, these are the pieces that came out, and you want one of these guys to cause a further reaction. That's a stable chain reaction. What is an atom bomb? More than one is causing a reaction. That's an atom bomb. Yeah. If more than one fission neutron induces further reaction, then the chain reaction will be uncontrolled. You have a nuclear explosion. Yeah. If less than one fission neutron induces reaction, the chain reaction will die out. The goal in a nuclear reactor is to ensure that exactly one of the 2 to 3 fission neutron causes further reaction, making the chain reaction stable. Yeah. What is the good thing about nuclear reactors? See, there, you maintain a chain reaction, and you don't have to shut down the nuclear reactor, only to refuel and stuff like that. So it's a nuclear reactor is on all the time. Okay? You invested $5 billion, and that $5 billion is constantly working. Even in a coal power plant, your $5 billion is working only half the time. And then on top of that, it spews carbon dioxide. You guys understanding the economics of it?
Thank you.
Yeah. So again, the absorption cross-section, so fission cross-section, what is the probability of a neutron causing a fission cross-section? And this is the neutron energy. If the neutron energy is high, the fission cross-section is low. So if you can slow down this neutron, this is in U-235 and plutonium-239, okay? If you slow down the neutron, then the fission cross-section can increase by a factor of 100. And so that's what you're doing, okay? That's what a moderator does. It'll slow down the fast neutrons to slow neutrons that'll cause further reaction. So important graph, okay? So again, here is the reactor vessel. There's the fuel assembly, moderator, slowing down neutrons, and control rods. You drop the control rods, they absorb neutrons, and they'll shut down the reactor. So very simple thing, a nuclear reactor. Yeah. Reactors are, so here's an important point. Reactors are typically designed to be about 99% prompt critical. What that means is 99% of the reactions are caused by the fast neutrons. Okay? The 1% that you need, okay, 0.99 neutrons, fast neutrons cause reaction, further reaction. The other 0.1% that you need, the 1% you need, are caused by the delayed neutrons. Okay. The additional 1% neutrons needed to reach the critical condition are delayed neutrons, and these are easily controlled on a time scale compatible with methods for adjusting control rods. Okay. So moderator material, these guys are slowing down neutrons. Commercial power reactors use one of 3 moderators: water, heavy water, or graphite. What is graphite?
What's in your pencil?
Yep, very good. Yep.
What is it? Sorry, I missed that.
It's what's in your pencil.
Oh,
Yeah. All right, so again, here's fuel core. You're producing heat by splitting nuclei. Here's water. Here's a so boiling water reactor and pressurized water reactor. There's a out of the 450 nuclear reactors, 300 are pressurized water reactors in the bowl. Okay. So you're producing heat, you pump water through it, which is act as a moderator and a coolant. This water turns into steam. The steam is turning blades in a turbine, and those blades, so the shaft is turned, and that shaft is turning the wire in the electric generator. The wire is sitting between magnets, and that's converting mechanical energy to electrical energy. Okay, so that's the reactor. How much of the heat got converted to electricity? 35%. Very good. And the rest of the heat has to be dumped out. Okay, you dump it in a lake or in the atmosphere. Air-cooled reactors so air-cooled reactors use air to extract the heat. So we built a lot of reactors in the 80s, and then it died down, and we're coming back up. There's been little growth. Okay, France gets 75% of its electricity from nuclear energy. Yeah. So world reactor capacity, again there's about, okay, so we are producing a gigawatt of electricity. Gigawatt is a Hoover Dam. About 400 Hoover Dams worth of electricity is being produced in the world using nuclear energy. Yeah. Again, this is very important. We've mentioned this before. See, the thing with electricity is you got to produce just as much electricity as you're using. So here's how the usage of electricity varies during the day. Okay, and nuclear reactors are best for this steady state need of energy. Okay, when usage goes to peak, right now we're solving this by using natural gas plants, and that's expensive. Okay, so if you had a little extra money for batteries, what you could do is you could build this many nuclear power plants, and when you have excess electricity, what do you do then? You charge batteries. Very good. Somebody's been listening. And then you use the batteries to run during excess time. Yeah? But your generation is much smarter. You're going to use solar, and solar and wind also produces electricity like that, except that this doesn't match that curve. So you're using whatever you're using, and excess you're using to charge batteries, and then you're using the batteries to run them. Okay? So if batteries were cheaper, all you'd see is solar and wind farms. Okay. You guys can read all of that. Again, here's relative risk. Nuclear power plants are extremely safe compared to those guys, according to these guys. Okay. The nuclear waste that can be contained in okay, so actinides are, okay, so here's when the uranium absorbs neutrons, you make heavier nuclei that have in fission. These heavier nuclei are from 89 to 103 atomic number. Only up to 92 are naturally occurring. So anything above 92 is man-made, and these guys are called actinides, and they can be radioactive so these guys can be radioactive for up to 100,000 years. You just bury them underground. Okay. So nuclear waste, okay, so all the commercial reactors ever operated have produced a total amount of high-level radioactive waste that's the volume of a cube 40 meters on the side. This building could contain all of the waste. Yeah. So your advanced reactor designs, so you see this is air cooled, okay? And these guys will never get too hot. These are air cooled. So with air cooling, you don't have the heat dissociating water to produce hydrogen, okay? And this heat is transferred to water here, okay? So this is a pebble bed reactor fuel element. Okay, you can read that. Okay, here. So again, this is a sodium cooled, liquid metal cooled fast breeder reactors. Again, nothing to dissociate and explode. Okay. So there are some of the designs. Okay. Thorium reactors. So thorium is naturally occurring non-fissile nuclide. However, it can be converted into fissile 233 by a neutron reaction, which is followed by beta decay. So thorium reactors are called breeder reactors. These are not fissile, but you can convert them to fuel. And the reason is thorium is much more abundant on Earth than uranium and can greatly extend the longevity of nuclear power. Okay. So you won't run out of fuel. Okay. All right, folks, you go home and build nuclear reactors, okay? Have them ready by next week.